In this video, we're going to start looking at particle dynamics, and this is chapter 9 on the lecture notes. Let's recap on what we have learned so far. Under the realm of classical mechanics, there are mainly three branches. We have kinematics, dynamics, and statics. Kinematic is what we have covered so far in this course, which is where we look at velocity, acceleration, angular velocity, and angular acceleration. So we use v as velocity, a as a general expression for acceleration, omega as the expression for angular velocity, and alpha as a symbol for angular acceleration. And we did not really consider the effect of forces. So what we have been doing with basic kinematic equations of velocity and acceleration expansion is we're trying to find the relation between velocity, acceleration, angular velocity, and angular accelerations. So now starting in chapter 9 or lecture 8, we're going to add forces and see how that's going to change our motion. So let me give you a little more background on the concept of classical mechanics. So Newton actually started the field of classical mechanics. Well, he's a symbol of the beginning of the classical mechanics, where he had defined laws of motion. And those are the three popular laws of Newton's, first, second, and third, which we'll go over in more details later on. And he also had a law of gravitation. Which describes the motion for celestial bodies. You probably don't know the fact that the law of gravitation is actually a simplification of the true physics. But this is close enough, and we can use that accurately to describe or estimate the motions of any rigid bodies, flexible bodies, and even celestial bodies. But on a grander scale, okay, so if we have a scale of size and a scale of speed, really we have four quadrants. We really have four quadrants of mechanics. So for classical mechanics, it really fits in at a slower speed. Whereas if we approach speed of light, we have to use general relativity, which is devised by Albert Einstein. So when we say higher speed, this is very close to the speed of light. Whereas when we talk about sizes, it's really any sizes that you can see or imagine. But if we have the sizes that are much smaller, then the physics are actually very different. And they used to describe such mechanism using quantum physics. And the other quadrant is something that I'm not too familiar with, but I'll just write down here. It's a quantum field theory. So really, classical mechanics fits in everyday objects. So we have anything that you can see and moves at relatively slower speed than speed of light. And you can actually accurately describe the motions of any object that's within this realm using classical mechanics. And classical mechanics is sometimes called Newtonian mechanics. So what are the three laws that Newton has proposed in his original Principia? So Newton's first law says everybody continues in its state of rest or of uniform motion in a right line unless it is compelled to change that state by force impressed on it. So if we're to simplify that and put in simple physics, if we have a zero force exerted on a body, then the body will have a zero velocity or have a constant velocity. Okay, so second law says the change of motion is proportional to the motive force impressed, and it is made in the direction of the right line in which the force is impressed. And this is the most popular ones that we have learned in physics, which is F equal to ma. So the forces you exert on an object is equal to the mass times acceleration. So Newton's third law says to every action that is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal but directed to contrary parts. Is if you have two objects, let's say this is the sun and Earth. The attraction forces exerted by the sun on Earth has an equal but opposite reaction force on the sun. And this goes the same for every object, and it applies to anything that may be further apart, which are affected by gravity, or something that you can touch upon. Say you're leaning against the wall. And let me draw a banana here. And if you're laying on the wall, you're actually exerting a force on the wall. But the wall also exerts a reaction force on you with the same magnitude, but opposite direction. So in this section, we're going to look at particle dynamics. So particle is really an oversimplification of any everyday object. But it's quite useful for us to describe and understand the concept of dynamics. So before we have looked at particle kinematics. And now we're going to look at particle dynamics, where we include forces in the equation. So in order to understand the motion, or better, let's use Newton's second law, F equal to ma. We need to understand what mass is. So mass is a measure of its resistance to change in motion. And notice the difference between mass and weight. Where mass is a physical property of an object, and it's a scalar. And you have the unit kilograms, slug, or pound mass. Whereas weight is not a physical property, but some forces that you feel or an object feel in a gravity field. We have already looked at accelerations, and we know it is the rate of change of the velocity of an object. Forces, if you recall from physics, can be in different forms. The definition of forces is the reaction or the interaction between objects, bodies. So every force is due to some interactions between two bodies. And for a given body, the forces exerted on it will change its motion. So there are mainly two types of forces. One is contact force, which are due to the direct contact between two bodies, and two is non-contact forces, which are exerted by bodies which are at a distance from each other and are not necessarily in contact. So some examples for such forces is gravity or electromagnetic forces. We can express a force as a vector. With a magnitude and direction. But for force, we also have to define where it is applied. So the point of application is actually very important because it is going to tell us at what point the force is exerted so that we can model the motions of the body. And we call those bounded vectors. And its definition is it's a vector which is associated with a specific point of contact. So if we're dealing particle dynamics, we know that the bounded vector is applied in the position of that particle. So we have some particle, P, and the force exerted on it would originate from point P. So this is what we call a bound vector, where you start the vectors at some particular point in this case, the position of the particle P. So consider that a particle is subjected to several forces, say F1, F2, F3, etc. And a simple sum would give us the total reaction force or the resultant force acted on the body. And so we have n forces, and we'll add all those n forces, and we'll get a sum of all the forces, which is the resultant force. So the sum of the forces is the resultant force acted on the particle. So again, to illustrate the concept, if we have point P, we have some force F1, F2, and F3. So we can express all the forces by just the sum of the forces. So F1 plus F2 plus F3. And you would have you can model the force as just one single force, as F sum of all the forces. From Newton's second law, we know force equal to ma. But we really haven't talked about the reference frames. If you recall, when we define the accelerations or find the acceleration of some point in an inertial frame or in a rotating frame, they would have a different value. So for Newton's second law, frame of reference is really important. And F equal to ma is only true in an inertial reference frame. So, in an inertial reference frame, we have the acceleration of a particle is always proportional to the resultant force on that particle. And this is illustrated by F equal to ma. And we can rewrite as acceleration equal to force divided by mass. So again, the acceleration of a particle in an inertial reference frame is proportional to the resultant forces on the particle and inverse proportional to the mass of the particle. So again, if we have the same amount of force, and the larger mass will result in a smaller acceleration. And you can replace the forces with the sum of the forces that we have defined earlier. Again, force F equal to ma is only defined in the inertial reference frame. And this is really a beauty of Newton's law of motion, is if we have a inertial frame, we can always describe the motion of a particle or object using Newton's second law, F equal to ma. Now you might wonder, how do we find an inertial reference frame? So for practical purposes or everyday application, you can actually define Earth as the inertial reference frame. However, for aerospace application, especially if we go on a larger scale, say the motion of the moon or the motion of planets, we'll have to use other reference frame that's originated at the center of the sun or the galaxy. So just for example, if you're trying to describe the motion of Earth, you can't really use Earth as an initial reference frame because it's rotating relative to the sun. So in order to accurately determine and describe the motion of the Earth relative to the sun, we need to find a reference frame that is fixed in the sun's inertial frame. And we know the sun is also orbiting around the center of the galaxy. Then to describe the motion of the sun relative to the galaxy, then we'll have to find some other reference frame that is fixed in the inertial space. So the definition of inertial frame really depends on the time scales that you're looking at the problem. So some facts about inertial reference frame. So if F is the inertial frame and G is a frame which translates in F with the constant velocity, then we have the acceleration of the point in G equal to the acceleration of the point in F. Thus we know G is also an inertial reference frame. So to define an inertial reference frame, we do not necessarily need to have an inertial point as the center of the reference frame. So that point can be moving in the inertial space at a constant velocity, and we can still say that's an inertial reference frame. And this is the result, actually the proof. If we have a G as a reference which translates with a constant velocity in F, we have the acceleration of some point in F equal to the acceleration of point P in G. So both F and G will be considered inertial reference frame. Now let's go back to look at some properties we have for resultant forces. Given that we have a 3 basis vector, B1, B2, and B3. And they can be in both rotating frames or inertial frames. And we have acceleration as the expression of A1, B1 plus A2, B2 plus A3, B3. Some of the forces would have some of the forces in the B1 direction plus the sum of the force in the B2 direction plus some of the forces in the B3 direction. Then we can get 3 scalar equations. Given that we know F equal to ma. So we know that the sum of the forces in the B1 direction will be equal to m times A1. sum of the forces in the B2 direction will be m times A2. Sum of the forces in the B3 direction is equal to m times A3. So essentially what this tells us is if we have sum of the forces, and just rewrite, is equal to m A1 B1 plus m A2 B2 plus m A3 B3. So you can see that in order to have two equal vectors, which is f hat and ma hat as the two vectors, we need to have every single component be the same. So we have the sum of the forces in the B1 direction equal to m times A1. We have sum of the forces in the F2 direction, in the B2 direction, as equal to ma2. And this is how we can get this relation. So basically, this equation states that the resultant forces in the ith direction equals the mass times the acceleration in that direction. So let's recap. We have three basis vectors, B1, B2, B3. And B1, B2, B3 can be any reference frame. It's either rotating or in the inertial frame. But when we define the acceleration vectors, the value must correspond to some acceleration in the inertial frame. Remember that when we define vectors, we can always use different reference frames. So this is the case where we use if we use B1, B2, B3 as a rotating reference frame, we're really defining a vector just in that vector basis. But A, the acceleration will correspond to the inertial reference frame. So we have some acceleration relative to an inertial frame, and we're just expressing that vector in the B1, B2, and B3 vector basis. So a special case for Newton's second law is static equilibrium. So the definition of a static equilibrium is a particle P is in static equilibrium if it is at rest in some inertial reference frame. We have the velocity of some point in the inertial frame equal to 0, where F is inertial. So the result is that if a particle is in static equilibrium, then the sum of all the forces acting on the particle is 0. We have the sum of the forces equal to 0. We can quickly see that if we take the derivative of the velocity upon P in the F frame with respect to the F frame, we get 0. And this is the acceleration of the point in the F frame. And we have defined F as the inertial reference frame. So if we use Newton's second law, F equal to ma, and a is the inertial acceleration, which is 0 in this case, then we have the sum of all the forces equal to 0. Now let's delve into more details on Newton's third law. where if two bodies exert a force on each other, they would have same magnitude but opposite direction. So this is a traction force, and if you have repulsive forces, they will still be at opposite directions. So as an example for attraction forces, and we have gravitational attraction, which states if we have two particles, M1 and M2, and they are at a distance r apart, we have forces that are exerted on mass M2 by M1, and the same force but opposite direction by M2 on M1. And we know the force is equal to the gravitational constant times M1, M2 divided by distance squared. So this is the universal law of gravitation. And this capital G has a value of 6.673 times 10 to the negative 11th m cubed kilogram per second s squared. Of course, you can do a dimensional check to find the dimension for the G from the above equation. Now, if we have a particle and a spherical body, and the particle is outside of the spherical body, so we have a spherical body M with mass M, and some particle with mass smaller m, and from the center of the larger particles to that m is the distance r. And if we assume the density at each point in the sphere only depends on the radial distance, which is, we know rho is just a function of d. So rho is the density, and it's a function of the radius only. Then we know you can actually prove with calculus the gravitational attraction on the particle is equivalent to F equal to capital G capital M times small case m divided by r squared. And r is the distance of the particle from the center of the sphere. And this is actually how you can describe a motion or the forces of a satellite exerted by Earth, because we know the mass of Earth to a rough estimate, and we know the mass of the satellite. If we know the orbiting altitude or the radius of the satellite from the center of Earth, we can calculate the forces, and then we know the velocity, and we know how the motion of the satellite is relative to Earth. Okay, so if we say the spherical body is Earth, then we have F equal to G times m of Earth times small case m r squared. And we know the mass of Earth is approximately 9.76 times 10 to the 24th kilogram. The one thing to notice is that the forces exerted on a particle m by some spherical object is always aligned in the direction. So this is the direction F exerted. And similarly, will exert a opposite the same magnitude F bar. So one thing we can quickly do is to estimate the gravity accelerations of an object on Earth. So we know F equal to G times capital M times small case m divided by the distance squared. And this is going to be equal to mass times acceleration. Notice that I just used the scalar case instead of vectors to find the acceleration of the particle. So we can quickly see the m can be cancelled out. So the acceleration of a particle under Earth's gravity is capital G m divided by r squared. And if we know the radius of Earth is 6.371 times 10 to the 6 meter. So for an object on the surface of Earth, the acceleration will be equal to 9.81 meter per second squared, or 32.2 feet per second squared. And we know the gravity acceleration is always directed towards the center of the Earth. So for most problems, you'll see you'll have some ground and some gravity vectors that's usually pointing downwards and perpendicular to the surface. And if we have some particle with mass m, the forces exerted by gravity on that particle is something we call the weight of that object. So its weight is something the object feels in a gravity field. And we know the weight is actually equal to the gravitational force and is equal to m times the gravity acceleration.